Hi there, guys. Well, welcome back. We're working towards 4n now, and 4n is about the second derivative and what happens to the second derivative around turning points, okay, or maxima and minima, as they're calling them here. Okay, well, there's a little box here which we'll just talk through to start off with, and let's just copy this one across. So just like there was a box in the previous one, by considering the first derivative around the turning points, we really need to make a little bit of sense of this as well. So it's saying, well, first of all, if we have this f dash of x is equal to 0, or f dash of c is equal to 0, at a particular c belonging to our domain, if we have this turning point essentially, then if the second derivative is less than 0, we have a local maximum. If we're putting in c into the second derivative, that is, and getting out a number which is less than 0. Now, we've discussed this before, but this is a much quicker way for determining whether or not we have a maximum turning point or a minimum turning point, or potentially a point of inflection as well. Okay, so let's unpack that a little bit. And the classic thing to do is to look at a cubic graph. And I've done this 2 videos ago, but just to say that your gradient is decreasing. Here we go, gradient is decreasing all the way until this point of inflection. So up until this point here, we have a decreasing gradient. Even though it's positive, it's becoming less positive. And less positive, and it's tending towards 0, and that's becoming negative, and that's becoming more negative, and that's going down all the way. Maybe that's a gradient of 5, and we're going all the way down to a gradient of -4. I don't know. On the other side, -4 there, where we have that point of inflection. Okay, so what we can say is that our gradient is decreasing throughout, and that's what the second derivative is talking about. This is saying the rate of change of our gradient. Okay, so if f dash dash of x is less than 0 when we're putting in this point c, then we know that the gradient is decreasing at that particular point. And that's going to be your point c there, which you're putting in. Now, it could be that you put in this point, and you could find out your gradient is decreasing there as well. And in fact, anywhere here, your gradient is going to be decreasing, because anywhere there, f dash dash of x is going to be less than 0, all the way up until that point of inflection. However, we're not interested in any point, we're just interested in the turning point, whether or not this is a maximum or minimum. So put c into the second derivative. If it's less than 0, we have a local maximum. If it's greater than 0, then we have a local minimum. You can see here that the gradient is increasing. In a similar way, gradient here is going to be increasing. So on this side, f dash dash of x, for any particular point you choose, on the other side of this point of inflection, there's the sort of break point there, you can see the gradient is going from steep negative to steep positive. It's going through 0 in the middle. So this is going to be greater than 0. So all we need to do is test c at the turning point, and if we find out the second derivative is equal to, I don't know, 10, 1, 100, as long as it's greater than 0, then the gradient is going to be increasing, and therefore we have a local minimum. Okay, so there's another little bit here. It just says if we have a turning point, or if we have a gradient of 0 essentially at this point c, and then if we find that the second derivative is 0, then the second derivative test is inconclusive for this maxima or minima. Let's just think for a second, where on this graph are we going to have f dash dash of c equal to 0? Well, up until this point, it's less than 0. Beyond this point, it's greater than 0. So in the middle, it needs to be equal to 0. It's where it changes from negative to positive. In other words, at points of inflection, okay, at points of inflection, for example, here, you're going to have the second derivative equal to 0. However, that's not the same as saying both of these conditions, f dash of c is 0 and f dash dash of c is 0, because we can see that we don't have a gradient of 0 there. We don't actually have a turning point. We have a point of inflection. Okay, so can we think of a condition where this exists? Okay, well, what about when we have y equals x to the power of 4? That one looks a bit like a quadratic. It's going to look like this. Now, we're going to get a turning point when we put in 0. So we'll get here, if we call it f of x, we can say f dash of x of 0 is going to be 0. So we definitely know there's a turning point. But also when we get the next derivative here, so first derivative of x would be 4x cubed. Second derivative is going to be 12x squared. We can see that when we put in 0 into this, we're also going to put out 0. So that's an example of the case where, although we can clearly see we have a minimum turning point, the second derivative test is inconclusive. Okay, so great if you found this, not great if you found this. So at that point, you're then going to need to think to go back to the first derivative test and then think, let's look at the first derivative, okay, and see if it's greater, gives us a gradient which is greater than 0 to the right hand side, and a gradient which is less than 0 to the left hand point, that turning point, to the left hand side, sorry, and then we can see whether or not we have a minimum turning point or a maximum turning point. So we're going to have to go back to the original test, which is exactly what they're saying here. Revert to the test that we have using the first derivative. Okay, right, but this is going to speed things up basically. So let's just make that a little smaller, and let's take the two questions here. So we've got example 27. So let's use the second derivative test to find the greatest and least value of this in this interval here. So let's do dy dx in terms of y, and we can see we've got 3x squared minus nx plus 7. And let's look at the second derivative as well. So second derivative here is going to equal to 6x minus 10. And we're talking about it in this interval here, in the interval between 0, 4. Okay, so first of all, we need to find out what our turning points are. That's what we're looking for. But let's just think about the question. It doesn't actually ask for turning points. It says to find the greatest and least value in this interval. Okay, well, we know we have a positive cubic. It's going to look something like this. And I'm expecting that we're actually going to find two turning points. But, it's quite possible that they've given us an interval here, which is like this. And that our greatest and least values might actually just be this point and this point here. Okay, so I'm expecting turning points within our interval, but we might not get them. So we have to be prepared that that might be the case. Now let's have a little look at this then. So we're expecting this one will factorize, but it would be fine if it didn't factorize and we just had to use the quadratic formula to get other real solutions to the roots of this. So we're trying to equal this to 0, of course, and what do we got? So we got hopefully 7. And I'm thinking 7 times by the 3 is going to be too large there. So I know it's got to be 7 and 1 or 1 and 7. If I put the 7 there, I'm going to get 21x. But I know I can't combat that basically from my other one. So I'm going to put the 7 there, put the 1 there, and then we're going to see we're going to get 7 times by 1. It's both going to need to be negative, and that's going to give us minus 10x, minus 7x, and minus 3x with those first and last. So that's our factorization. Now, again, you've got a long method of factorization. You can use it if you want. You should have that at least, where you say 3 times 7 equals 21. Now solve the puzzle of two numbers timesing together gives you 21, and two numbers adding together minus 10. And then that's how you're going to split your middle term. Okay, but either way, This one was pretty easy to do by going commando. So just, figuring it out. Okay, so your two solutions from this is going to give you two turning points, in fact, and that's going to give you x is equal to 1 in the easy bracket first, and x is equal to 7 over 3. Now, both of those are in this interval here, so I actually know that 0 is over there and 4 is over there. This is x is equal to 1, and this is x is equal to 7 over 3, which is 2 1/3. Okay, so there's 1 and there's your 2 1/3. I know it's going to look like this. Now, greatest and least values in this interval, it's still possible that this is lower than this. Okay, we don't really know from that sketch. And it's still possible that this is higher than this. We don't know. So we're going to need to check both of those things. So I'm going to just start off by bring over to the side. When x is equal to 0, what's y equal to? We can see that that's just going to be equal to 0. There's essentially a plus 0 on the end here. All of those terms are going to become 0. So we know we've got this as our point on this end. And let me just get rid of this function here because it's going to in our way later on. So we've got the coordinate point 0, 0 at the start, and we've also got the coordinate point 4, comma, we need to put 4 into this as well. So we've got, what's that, 64, take away 5 lots of 16, which is 80, and then plus 7 lots of 4, so we've got plus 28 there. So what's that giving us? That's giving us 80, it's giving us 12, isn't it? So we're getting 80, 92, so 12, okay. So that's giving us 4, 12. Again, I'm just putting those aside because I'm going to need to check my turning points against those later. Okay, so use the second derivative test. So now I need to put this in here to determine whether I've got greatest or least values. Well, I don't really, because I know I've got a positive cubic. But, this exercise wants us to use this second derivative test. So, okay, well, we're going to have to do it. We say, well, when x is equal to 1, the second derivative is equal to 6 take away 10 is equal to minus 4, which is less than 0, which tells us that we have a maximum turning point. So it's sufficient for us just to write max TP. Okay, TP, not toilet paper, turning point. And then when we have x is 7/3 there, we've got this thing here is equal to, we're chucking that in here, and 6 lots of 7/3 minus 10. What are we getting? 42 divided by 3 is going to be bigger than 10, so this is greater than 0. And so therefore we have a minimum turning point. This implies that we have a minimum turning point. Okay, right, so now we've used the second derivative test, but we do need to do a bit more because we actually need to check the heights of those functions as well at that point. So when we get x is equal to 1, we need to substitute it into here. And so that's giving us, not there, sorry, here. And that's going to give us 1 take away 5 plus 7. So that's giving us 3. So y is equal to 3. So that's our new point. We've got 1, 3. And then when we've got, when we've got x is equal to 7/3. Excuse me, but I'm going to have to just do this on the calculator. We've got, okay, tell you what, let's just pause this one off. Okay, so we're getting the answer of 49/27. Okay, and a little tip on one of your older style calculators, that if we're substituting in fractions into this expression here, then what you can do is store your fraction. You can say, well, let's store this as a, and then when you type this in, you can just say we've got a cubed minus 5a squared and so on. Just saves you from the fiddly creating of brackets and putting in your fractions as well. Okay, so 49 over 27. So we've got now 7/3 and 49 over 27. And now you can see that we have greatest and least values here. We're looking for the y values, which are greatest and least. So least value here is equal to 0, it would seem. And the greatest value is 12. Okay, that's interesting. So at 0 and at 4, it's actually at the ends. It's not in the middle where we have the, maximum values in this function, okay? So let's have a little look. So we had 0, 0 here, so at 0, and then we had something happening at 1, something happening just over halfway at 2 and 1/3. So we're getting out 4/12 is going to be up here. That's going to be our highest number. There's 12. We've got 0 off here, and then we can see that we've got 1, 3. So it's going to go something like, there's maybe 3. So it's going to go something like this, this, this. Okay, and this 49 over 27 should be a little bit lower than our 3. So that checks, but it's not as low as 0. Okay, so the answers are essentially this one and this one, 0 and 12. Okay, well, let me do that on Desmos as well, but let's also see what the book says. The book says at 0, yeah, y is equal to 0, and x is equal to 4, y equals to 12. Okay, so there you go. There you go. That's done. So we just need to consider the endpoints there. That was kind of important. That although we found local minimums and maximums, we didn't find our global extrema. So in fact, the endpoints were the global extrema in this case. Right. I think I've said that several times now. Let's just put this function in. So we had x cubed minus 5x squared. Let's put it into Desmos. Okay. Desmos. We've got x cubed minus 5x squared, and what was the rest of it? We had plus 7x. Plus 7x should go start there as well. And you see it can actually type this in without actually defining this as y, but there we go. And then if we just say in our range here, so if we define this to be between 0, x, and 4, there we go, there's our function in the end. Okay, let's just zoom out. That's what we've got. That's what we found out. Okay, so let's do the next example. So next example and last example for exercise 4N, we've got example 28. Okay, so it says find any turning points of y equals x minus 5 all over x and state the intervals where this is increasing or decreasing. Okay, well, when you look at this, you might think this is a quotient of functions, but you can make it simpler than that. Hopefully you can think about how you can make it simpler there. So here we go. We can split this into two fractions. It's going to be a 5 over x. So we can say that this is 1 minus 5x to the minus 1. Okay, find any turning points of this thing. So let's work out y dash, if you like. So we've got the y, the x. 1's going to disappear. By the minus 1 gives us plus 5, and then reduce the power by 1. So that's dy dx. And then the second derivative we're going to do here is going to be minus 10 x to the power of minus 3. Okay, so times by the power and reducing the power by 1. Now, it's probably easier to write this in the format 5 over x squared. And we need to try and solve when does that equal to 0. Now, when does that equal to 0 to find our turning points? Well, if we've got a non-zero numerator for a fraction, then we can never get a 0 for this fraction. For a fraction to be equal to 0, you have to have 0 over something is equal to 0. And now, if we've definitely not got 0 on the top, we can tend towards it, but we can never get 0. So there are no turning points. So if there are no turning points, we can state that. We've got this implies no TPs because there are no solutions. Okay. So it's still asking, state the interval where y is increasing. So now we need to think, where is dy dx greater than 0? We can see, in fact, this is not going to be interesting to us. We're just interested here in looking at where the gradient is greater than 0. Where the gradient is greater than 0, we can see that we have an increasing function. And as soon as that changes, as soon as the gradient becomes negative, then we have a decreasing function. Okay, so for what domain essentially, or what interval do we have where y is increasing? Well, we need to solve this. Well, hang on, when we try to solve this, we've got 5 over x squared is greater than 0. Now try timesing across by x squared, and you've got an issue. Because that's going to be equal to 0, so that gets rid of our x squared there, and we can't solve this thing. Well, to be honest, I think you can probably just say instead that, let's just think about this one. It's saying, well, we've got 5 over x squared. Well, x squared is always positive, no matter what you put in, positive or negative numbers. So this is greater than 0, and you could say, since x squared is greater than 0. So since x squared is greater than 0, this has got to be equal to 0. And therefore, this is giving us an always increasing function. It's increasing for all x belonging to your real numbers, apart from, of course, this is not defined when x is equal to 0. Okay, and I think that's a sufficient explanation there. Now it says sketch the graph. So I think if I was going to do this, I would, and I didn't have access to a calculator, I would simply do my transformations from my reciprocal function here, just as we've done in former units. Okay, so I would just do that. And of course, the information which we have now tells us that we don't have any turning points and that we have an increasing function throughout. We also know that we have a vertical asymptote when x is equal to 0. And we know as well that this could tend to 0 when we're tending x to infinity. And so we're going to have a horizontal asymptote of y is equal to 1. Okay, so let's just sketch the graph out again. So we've got y equals 1 minus 5 over x essentially. And let's start with the function 1 over x. So 1 over x is looking something like this. Again, it's going through that coordinate point 1, 1. And then timesing by minus 5 is going to take this point, so it's going to stretch it. I suppose let's stretch it like this. And, it's going to stretch it so it's going to go through the coordinate point 1, 5, and everything else is going to be 5 times as high. And it's going to, the same is going to happen in the other side. And this is a terrible drawing, by the way, because they should tend towards, never curve backwards. And then you're going to have the same situation happening on this side as well. And then when we're going to take minus that, it's going to flip to the other side. And then we're going to need to add 1. Okay, so your final graph could look like, you're going to have that horizontal asymptote of 1. We're going to have the graph flicked around the other way round here, so it's going to go something like this and something like this. It's going to look something like that, tending towards the y-axis up here, and we're going to have our vertical asymptote here as well. So we should state what our asymptotes are. So our asymptotes are going to be equal to y is equal to 0, no, y is equal to 1, and x is equal to 0. And I would put on a coordinate point here as well. So this coordinate point here, 1, 5, would become the coordinate point 1 minus 5 when you take it further down. And now it's going to go up by 1. So you're going to have the coordinate point 1, let's put it there, 1, comma, minus 4 here when you add on the 1 at the front. So this is going to be 1, comma, minus 5. And I would just track a point, an obvious point around. And, you know, let's put in y equals 1 there. We can put in x is equal to 0 there. And we probably should say where this crosses the x-axis as well. So when we set y equal to 0, we'll see that we get 5 over x is equal to 1. So we're seeing that x is equal to 5. So we know that this is the coordinate point 5 here. So we should show where it crosses the axes here. It's crossing it in our, you know, in sort of the reasonable bounds of our zoomed in window here, if you like. Okay, let's have a look at what the book does. There we go. I think it probably just takes it from the GDC. So that's probably what they're expecting you to do anyway. Okay, so there we go. There's the function. And yeah, there we go. That's done. And now we're going on to 4N. There's 4 questions there. And let's have a look to what's happening next time. We're talking about points of inflection next time round. So we've done a bit of that already. We're going to formalize that next time round. Okay, guys. Well, thanks for listening and good luck with the exercise and hope to see you back next time.